If you've ever been in a science classroom, you may have seen a poster that looks like this. It's the periodic table of the elements, and this is the topic of our video. But before we get to the nuts and bolts of the periodic table, it might be a good exercise to review why we use tables in the first place. You may have recorded a simple t-chart to group values, say x and y that belong together, and you may have used this table of values to plot points on a graph to help interpret the relationship between the variables in your table. We do this all the time in math classes, and we can expand the table if we want to compare similar relationships for different objects. This happens frequently in most science classes. We can even take complex problems like climate change and interpret tables of data to help us explore the deeper relationships in visual ways, perhaps to understand the problem and find meaningful solutions. Now, the periodic table of elements encapsulates all the stuff we know in nature, and of course this table will be a little more complex than a simple t-chart. So let's start by building one. Now, just like any table, it's a systematic way of recording data in rows and columns to group information in a meaningful way. But in order to capture the complexity of all the matter we know, we'll have to include a few twists. For now, let's just build the first 5 rows of the table. We'll add more a little later on. And once we have the table structure, we need to determine what information we'll record and how. The first thing we'll record is the symbol. That's a unique 1 or 2 character shorthand we use in chemical formulas for things like the water we drink, the carbon dioxide we exhale, sugars we use for energy, or the fuel we can burn to stay warm. And the symbol should reflect the element name by using defining letters in the name. But you need to be mindful here. Sometimes the letters are taken from the Latin translation of the name. Perhaps scientists just like to do this to sound smarter. Like Na used for sodium in the first column and third row is from the Latin natrium. Now the elements are arranged in order of their atomic number. We'll see that this plays a part in describing the atomic structure of each element, which is linked to its chemical nature. Now below the element name we find the atomic mass. It's important to know that the mass of any atom is always a whole number with no decimal, but we'll see later how different atoms of the same element can have different masses. The value recorded in the periodic table is the average value of any significantly large number of atoms measured together. And finally, we'll consider the ion charge. Now this is not in all periodic tables, but it's a helpful value when determining how elements will combine to form compounds. Now each element has a unique set of data distinguishing it from the other elements. So let's complete the table with the information for each of them, and we'll see patterns emerge like the large group of metals that occupy most of the periodic table. Then there are the nonmetals toward the right side, and finally the metalloids or semimetals in between these two groups. Many versions of the table will indicate the state the element occupies at room temperature. Most elements are in the solid state, but bromine is a liquid at room temperature, while a number of the nonmetals are naturally found as gases. Now to complete the table, we have to add 2 more rows. The most current tables have 7 rows, and the last 2 rows have additional elements, which would make the table too wide to fit on standard paper. So most tables remove a section from these rows and include it below the rest of the table as shown here. In fact, the 7th row was just completed in December 2015 with recently discovered elements. The names chosen for them are nihonium, moscovium, tennessine, and oganesson. These should be approved by November 2016, but it'll be a while before standard tables are updated. Now those groupings we saw earlier are quite large, and memory experts show us that making groups smaller allows us to remember things more easily. This is sometimes referred to as chunking. A good example of this is how we write phone numbers. Now I'm located in North America where phone numbers are 10 digits long, but we break them into groups of 3 or 4 numbers. The first 3 digits is the area code, while 2 of the next 3 digits was historically the exchange. That's the building servicing a specific region within the area code. And finally, the last 5 digits uniquely identify each phone within each exchange. It's this chunking that helps us remember phone numbers more easily. Just think of the way you almost sing the number in your head as you try to remember one. And it doesn't matter where you're located. While the chunk size can vary around the globe, this chunking strategy is universal. Now the elements are organized in a way that makes it easy to chunk sections according to their chemical nature. On the left we have the alkali metals that all react quite violently, even with water. Next to this group are the alkaline earth metals, which still are very reactive, but a little less aggressive than the alkali group. Each family tends to form similar compounds with elements from other groups. Continuing to the right, we have the transition and basic metals. These metals often form multiple ion states and can combine in different ways with the same element. Then we have the semimetals or metalloids that can behave like metals under certain conditions, but like nonmetals in other chemical circumstances. The second group from the right of the table is a subset of nonmetals known as halogens. Like the alkali metals, these also tend to form violent reactions. And finally, we have the noble gases. These are elements that tend to be non-reactive. Gases like neon and argon are often used in light bulbs as they can be heated and even glow without reacting. And of course there's hydrogen, the simplest and most abundant element in the universe. A number of periodic tables separate hydrogen from the rest of the table slightly, as it has unique chemical properties. Another feature of the table's organization is the rows, which we refer to as periods. In each period, the chemical behavior of the elements changes, but as the atomic number advances from the end of one period to the beginning of the next, the transition between chemical families tends to repeat. When a pattern, like the changes in chemical properties, repeats, we refer to this pattern as periodic. To get an idea of this periodicity, just think of each week starting on a Sunday, then advancing to Monday. The week continues through to Saturday, but the next day is Sunday again, and the pattern repeats. The group numbers along the top of the table also allow us to sort through the elements. Remember that the different element families tend to share common columns or groups, and each element, like sodium or carbon, occupies a unique period and group combination. This will help us determine the internal structure of elemental particles we call atoms. The word atom means indivisible, but it turns out that atoms can be divided into subatomic particles. The relatively heavy and positively charged proton, the equally negatively charged but very light electron, and the neutron, which has no charge but does add mass like the proton. A picture that helps us understand the inner structure and the chemical nature of the elements is the Bohr-Rutherford model with a nucleus containing the atom's protons. The number of protons is always equal to the element's atomic number found on the periodic table. Outside the nucleus, electrons travel randomly in space but at specific energy levels, sometimes referred to as orbitals. The first two electrons always exhibit the same orbital, but a maximum of 2 electrons can share this energy. Additional electrons must travel around the nucleus at a higher energy level. Each orbital has a specific energy, and only a fixed number of electrons could potentially share that energy level. The number of orbitals in a given atom corresponds to the period where we find that element, and the group number at the top of the table indicates the number of electrons in the highest energy level. These electrons are called valence electrons, and play a crucial part in ion formation and chemical bonding. And finally, the neutrons are also located in the nucleus. The number of neutrons can vary from atom to atom, giving us different isotopes of an element. For example, the most common isotope of carbon is carbon-12, with 6 protons and 6 neutrons. Heavier carbon isotopes, like carbon-13 and carbon-14, just have additional neutrons to provide mass without changing the atom's chemical properties. Now, it's important to note that the Bohr-Rutherford diagram indicates electron energy levels and not their physical motion. Their motion is best illustrated with clouds that look like this. So let's use the periodic table information and the Bohr-Rutherford model to look at ion formation. Sodium and chlorine can ionize and combine to form table salt. Both are in period 3, so each has 3 orbitals. Now sodium's atomic number is 11, so it has 11 protons, while chlorine, whose atomic number is 17, has 17 protons. Since neutrons don't affect the chemistry, we'll omit them from our diagram. Well, for each atom to start out neutral, as matter appears to be in nature, we need the same number of electrons as protons for each. Electrons will populate orbitals according to their capacities that we showed earlier. Now a stable ion forms from an atom when that outermost orbital is complete. When the valence orbital only has a few electrons, it's easier to remove the valence electrons, leaving the next lower orbital, which is complete, as the outer orbital. But if the valence level is close to capacity, it's easier to add electrons to complete the valence orbital. Now adding or removing electrons leaves ions with a net charge. Adding electrons makes an ion negative, which we refer to as an anion. But removing electrons makes the ion less negative, or simply positive. We refer to positive ions as cations. So our sodium cation has a charge of +1, while our chloride anion has a net charge of -1. We'll learn later how to use this information to understand chemical bonds and reactions.